If you've worked with hydraulics, you've likely seen how fast things can go wrong when a system fails. After 30 years in the field, I've seen the same mistakes repeated again and again. In this video, I'll walk you through 7 common hydraulic design and maintenance mistakes that damage equipment, overheat systems, and cause costly downtime. Welcome to Electrical Lad. If you're new here, hit subscribe so you don't miss future videos. So let's get started. Mistake number 1. Oversizing the pump and using flow control to achieve the correct speed. Don't get me wrong. I'm not saying you should never use flow control valves. They're actually needed for fine-tuning the speed. Let's say the actuator needs 5 gallons per minute to extend at the correct speed. But the hydraulic pump is a positive displacement gear pump putting out 20 gallons per minute. That means you're forced to restrict the flow by 75% just to get the speed right. So what's the problem with this setup? The number one issue is that when the valve shifts, the restricted flow creates a sudden spike in back pressure, even though it's flowing to the tank. This instantaneous back pressure causes system shock. Over time, this shock can lead to damage in the actuator, seals, fittings, and even the hydraulic lines. The other big problem is wasted energy and heat. A 20 GPM pump running at 1000 psi requires about 13 horsepower. But if the system only needs 5 gallons per minute at that pressure, then a 5 GPM pump would only need around 3 horsepower. That means you're wasting about 10 horsepower just turning it into heat. This extra heat raises the hydraulic oil temperature, which means you'll need a larger cooler or risk overheating the system. So how do we solve this problem? To fix this problem, you have 2 options. One is to replace the pump and motor with the correct size that matches the required flow and horsepower. The other and more efficient solution is to use a variable displacement pump. A variable displacement pump automatically adjusts its output to match the system demand. This way, it only produces the flow needed, reducing energy waste, lowering heat generation, and improving overall system efficiency. If you're not familiar with hydraulic symbols or how to read a schematic, I recommend watching my other video, 30 Years of Hydraulics in 17 Minutes, before diving into this one. I've also added some helpful resources in the video description if you want to learn more. Mistake number 2. Increasing pressure to gain speed. This is one of the most common misunderstandings in hydraulics. Many technicians and operators mistakenly crank up the pressure setting, thinking it will make the actuator move faster. But here's the truth. Pressure does not control speed. Let's say your system is lifting a 10,000-pound load. It takes 800 psi to lift it, and your relief valve is set at 1000 psi. When you shift the valve, the gauge shows 800 psi, not 1000. Why? Because the system only builds the pressure needed to move the load. The relief valve doesn't open because the pressure never reaches its setting. It's just a safety backup, not something that controls normal operation. Now let's say the cylinder is moving slow. So someone increases the relief valve setting from 1000 to 1200 psi. But when the system runs, the pressure still stays at 800 psi, and the speed? Still slow. Why? Because pressure has nothing to do with speed. Flow does. And even if the load did need 1200 psi, raising the pressure limit still won't change the speed. It helps to lift the load at the same slow speed. Not unless you increase the flow rate. So, why might flow be low? There are a few common reasons. The pump is undersized, worn out, or just not putting out enough flow. The pressure filter might be clogged, restricting flow to the system. Or a flow control valve is set too low and limiting the actuator speed. Always fix the flow issue first and do not touch the pressure setting. Mistake number 3. Controlling an overhung load with a flow control valve. I've seen this mistake many times, especially with newer engineers, thinking that a flow control valve is enough to handle an overhung load. Let's talk about overhung loads. Unlike horizontal loads, you can't use the same circuit design for overhung loads because gravity plays a major role here. Imagine a 5,000 pounds load hanging from a cylinder in this example. When the directional valve is energized to lower the load, it free falls, much like dropping a heavy stone from the top of a mountain. This happens because the rod end of the cylinder's port shifts to the tank with no resistance to counteract the gravitational force. You might wonder, why not use a flow control to slow the free fall? The problem is, if you reduce the flow too much, it builds up high pressure at the rod end of the cylinder, which can damage the packing. To exaggerate this, imagine the flow control is fully closed. The pressure could skyrocket to 1000 psi, plus the full weight of the load bearing down. With nowhere for the oil to go, all that force piles up on the packing like a pressure cooker ready to explode, eventually causing it to fail. So, how do we solve this problem? The solution is coming up next. The answer is a counterbalance valve. It's a normally closed pressure control valve designed to balance or counteract a load. The pressure is usually set to create a force equal to or slightly greater than the overhung weight. This pressure is calculated based on the rod end piston area and the weight of the load. If you have any questions about counterbalance valves or how to calculate the pressure settings, feel free to drop me a note in the comments. Mistake number 4. Not having a way to drain the accumulator. This is one of the most dangerous mistakes I've ever seen. There are documented cases where it has led to serious injuries and even fatalities. It's not just a design flaw. It's a safety hazard. Think of hydraulic accumulators as backup batteries for hydraulic systems. They store pressurized fluid and release it when needed. But they can also be dangerous if not designed properly. Why? Because they store fluid energy. When the system is shut down and in a zero-energy state, there must be a way to safely drain the accumulator back into the tank. If not, there's a risk that someone might accidentally energize a valve, causing unintended actuator movement, potentially leading to serious injury. In this circuit, we have a solenoid-operated normally open two-way valve that connects the accumulator to the tank. This setup ensures the accumulator can only be pressurized when the valve is energized, as energizing the valve blocks the drain port. A manual two-way valve can also be used to drain the accumulator into the tank when the system is shut down for maintenance. Mistake number 5. Using only directional spool valves for clamping. In some applications, like clamping a mold or keeping a bus bar switch closed, you need to hold the force for an extended period. But relying only on a directional spool valve to hold the pressure is a risk. Why? Because spool valves are metal-to-metal inside. They don't seal perfectly in the center position. Over time, that internal leakage gets worse. So if the valve is held in center for too long, it won't hold pressure and the clamping force decreases. It might even drift. So what is the solution? To solve this problem, install a solenoid-operated check valve on the blind end of the cylinder. When the cylinder extends, the check valve blocks any fluid from leaking back through the directional valve, so the clamping force is held securely. When it's time to release the clamp, simply energize both the solenoid check valve and the A side of the directional valve. That opens the path and allows the fluid to return, releasing the clamp. Mistake number 6. Using flow control or flow restrictors with proportional valves. I have seen this problem once, but it wasn't so obvious and caused all kinds of performance issues. Proportional valves are designed to precisely control flow or pressure based on analog signals from the PLC or other control devices. In most systems, the PLC program controls the analog output, usually a 4 to 20 milliamp signal. That signal feeds into the proportional valve driver, which adjusts the valve position accordingly. This allows the PLC to control flow or pressure, depending on the type of valve being used. It's a precise way to control motion, force, or speed in real time. But when you add a flow control or a needle valve downstream, you interfere with the valve's ability to respond correctly. You get pressure buildup, flow instability, or even erratic actuator movement. It defeats the purpose of using a proportional valve in the first place. If you need to control flow, let the proportional valve do the job it was designed for. Don't choke it with a manual restriction. Mistake number 7. Not using a pressure line filter with a proportional or servo valve. Most hydraulic systems typically include a return filter that cleans the oil before it flows back into the reservoir. However, proportional and servo valves have tight internal clearances, often just a few microns. Even small amounts of contamination can cause them to stick, drift, or fail. And if the pump fails, metal fragments can flow straight into the valve, causing instant damage. That's why a fine pressure filter, 10 microns or better, should always be installed upstream of the valve. Without it, you're risking instability, breakdowns, and expensive repairs. These 7 mistakes are common in real hydraulic systems. And the truth is, most of them are avoidable. It just takes more attention to detail and better design practices. If you found this video helpful, please share it, subscribe to the channel, and hit the like button. See you on the next video.